Chapter 7, area of a region between two curves. Remember what the definite integral represents. Area of a region bounded by a given function, the x-axis, and the vertical lines x equals a and x equals b. I know it's bounded by the x-axis because I'm integrating with respect to x. If we think about splitting this integral up, geometrically what would be represented by this? Area bounded by f of x minus the area bounded by g of x. So we're finding some region and then we're taking another part of it away. Graphically, let's look at these parabolas. We'll call this g of x. And we'll call this function f of x. So if we want the area of the region bounded between these two functions, well, what would that represent with the integral? G of x would be the region between the x-axis and below the parabola in red. And if we take away the region bounded by f of x and the x-axis, it would be the region in between. A helpful hint or that your book uses to represent the boundaries, it refers to what is called a representative rectangle. So we drew the rectangle up and down, which tells us that we're going to integrate with respect to x. And if you think back to the beginning of chapter 4, before we defined the integral, we found the area using geometric properties, or we used area to approximate it with Riemann sums. What this represents is we know how to find the area of a rectangle, length times width. So we know the width is in terms of x, and then the length or the height, it would come from this function minus this function. So area of a rectangle is length times width. Alright, the length comes from, again, the top function minus the bottom function, and then the width is in terms of x. So this area formula, a to b g of x minus f of x, or f of x minus g of x, it just represents two functions. Both functions must be continuous. And they're continuous on the interval from a to b. So no discontinuities, no breaks in the graph. And furthermore, what we're calling here f of x has to be less than or equal to g of x. Okay, so there has to be a function where in this interval all the y values of the function we're calling g are bigger than or equal to these values, the y values of this function f. And then where do the bounds for integration come from? They're from the points of intersection. So we would solve where the functions are equal to each other. Alright, let's look at some examples. Given this function, x squared minus 6x, draw the representative rectangle. And again, that's just a guide to tell you what you're going to integrate with respect to, x or y. You don't need to do that always, but when we talk about volume, that becomes helpful. Set up the integral. So the area would be the region bounded between this function is y is equal to 0. That's the top of the representative rectangle, minus the bottom function is the quadratic. Now this is easy enough to see, but we'll do it anyway. To find the boundaries, to find the values of a and b, we set the two functions equal to each other. And this is graphed to scale, so it's easy enough to see that 0 and 6 are where the two functions intersect. Distributing the negative. So now to actually evaluate or find the area, we integrate the function. And from 0 to 6, now without the aid of a calculator, let's try and, that reduces to 2, negative 72 plus 108, so the area of the region is 36. As a rule of thumb, if we're talking about area would be non-negative. If you got an answer of negative 36, then your function was incorrect. That would be, you may have taken the parabola and subtracted the line y is equal to 0. But think, on this function, all my y values in this region are negative. That's why the horizontal line y is equal to 0 is our top function. Okay, now without the aid of a graph. Find the area of the region bounded by these two functions. So first we want to find our boundaries, our points of intersection. Now I would not suggest expanding that binomial. If I subtract that term from the right hand side, now I can factor out an x minus 1. And I know you're thinking, I would never think to do that, but that's why we do it together. First, double the product, square the last. Alright, so we have several things going on here. One, there's 3 points of intersection. 3 points of intersection will be your indicator that your top and bottom functions switch in the interval. So if we want to perhaps look at a number line, let's put 0 here, 1, and 2. What you need to determine is which function is your top function, which one is your bottom function. And when I say that, I mean which one. Let's not use f and g, but the integrand has to be set up top minus bottom. So which y values are bigger? Alright, so if we choose a value less than 0, if I plug negative 1 into my functions, f of negative 1 gives me negative 8, and g of negative 1 wait a second. I messed up. So these functions are equal at 0, 1, and 2. So the region that we would be integrating, we're going to be integrating from 0 to 1, and then we're going to integrate from 1 to 2. On these intervals, you need to determine which function is top, which one is bottom. So if we plug in, say, 1/2, f of 1/2, it would give me negative 1/8. G of 1/2 would give me negative 1/2. So which function would be on top? F would be on top. Negative 1/8 is bigger than negative 1/2. So this integral if I test 1/2, I would get positive 1/8 in F and positive 1/2 in G. So now which function is bigger on the interval between 1 and 2? 1/2 is bigger than 1/8. So the line would be on top of the cubic. Alright, now let's set up the integral. So between 0 and 1, top minus bottom. And then from the interval from 1 to 2, line is above the cubic. Find the answer. You have to do these separately. Integrate the function, plug in the boundaries, and we'll talk about the answer. Alright, now look, our integrals in terms of y, but we can treat it the exact same. So we're going to integrate with respect to y, because our functions are in terms of y, but all of the entire process is the same. Find the points of intersection by setting the functions equal to each other. Y minus 2, y plus 1. Okay. So between negative 1 and 2, these represent our boundaries. Alright, so let's pick y is equal to 0. So f of 0 would be 0. G of 0 would be 2. So the line is bigger than the quadratic on the interval from negative 1 to 2. So when we set up the integral from negative 1 to 2, g of y minus f of y. Alright, so that's the integral from negative 1 to 2. Y plus 2 minus y squared. Nothing to combine here. So integrating. 2 squared is 4 over 2 plus 4 minus 8/3. And then 1/2 minus 2 plus 1/3. Alright, so we have 8 minus 3 minus 1/2. 9/2. Now you getting from here to here and then your final answer without the aid of a calculator, just do whatever's easiest. I subtracted these, that's where the negative 3 came from. 6 plus 2 gives me 8, so 9/2 is the answer. Alright. In the interest of time, let's look at this one. Sketch the region bounded by the graphs and find the area. Y is equal to 0. That's the x-axis. 1 over x squared. We know that that graph is in the first and second quadrants, but we're not concerned with the second quadrant. X equals 1, x equals 5. So we're looking for this region. So the integral from 1 to 5 of 1 over x squared dx. Integrating the function, negative 1 over x from 1 to 5, negative 1/5 minus negative 1. So the area would be 4/5. Okay, we'll continue a discussion of this in class tomorrow. Have a nice night.